Alright guys, today we're going to talk about the atom. Now, what the atom is and kind of how it came about was these discoveries of just people doing different things, and it might look like something disappeared, but it actually wouldn't. And one of those examples you can do just at home. If you have a tablespoon of sugar or even of salt and you put it in water and stir it up, it looks like that sugar or that salt will disappear, but if you taste it, obviously the sugar is still there, or obviously the salt's still there, and you can just kind of see it. And so they kind of had this idea that matter, or the things that we can touch and feel and everything else like that, are made up of these little tiny particles, and there's some rules that kind of govern them. Now, the foundations of this, came about a long time ago, and there's really three main ideas that have to do with all that. The first one is what they call the law of conservation of mass. Now, what the law of conservation of mass says is that matter and mass in general can never be created or never be destroyed. And, that's going to say that, like with that sugar, and you stick it in that water and stir it up, the sugar doesn't actually disappear, it's just been dissolved, or it's still in that water somehow. Okay? And, the same way that if you have some salt water and you let all that water evaporate in the sun, that salt is still there. It didn't just be created, it was there the whole time, and just it was separated kind of with that. So there's this idea that you always have this law of conservation of mass, that it doesn't actually poof disappear or poof appear. Okay, that's the first one. Now, the second kind of main idea that we have is this law of definite proportions. Now, this is kind of getting a little bit heavier with all this stuff. What that's going to say, though, is that a chemical compound will have the exact same elements in the exact same proportions, regardless of how big or small that sample is. And kind of the example of this is you take a sugar cube, right? Oh no, it's yay big by yay big by yay big. Or you just have like a sprinkle, a tablespoon of sugar, and you have all the individual little ones. When you're looking at the sugar, that compound will have exactly the same number of atoms of each type of element. In sucrose, which is just a simple sugar, will have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Well, it's always going to be that 1 to 2 to 1, right? 6 to 12 to 6 would be 1 to 2 to 1. It's going to have that exact same ratio regardless of how big the sugar sample is, okay? It could be a really large sample or a really small sample, but it's just this idea that they're always going to have that same ratio. And our third one that we kind of want to talk about, I think it's up here, yep. Okay, this one's a little bit bigger. I know, it's a lot. Okay, it says the law of multiple proportions. Now, that says that if two or more different compounds are composed of the same two elements, then the ratio of the masses of the second element combined with a certain mass of the first element is always a ratio of whole numbers. And that's kind of like I was saying, that this idea, H2O, right? Those are simple numbers. You're not going to have half of a hydrogen, or you're not going to have half of an oxygen. And I'll explain this one a little bit more in just a little bit, but it's just this idea that we have the same two elements that are always going to have a small whole number ratio to each other. All right? Okay. So I know that's a lot, and that's kind of where we started with all of these things. Now, in addition to all of that, we had this idea from a guy named John Dalton, and what he did is he proposed this explanation for the law of conservation of mass. Okay, remember this guy up here? Mass is neither created nor destroyed. And he thought that the elements were composed of atoms, and they only combined to form, different ones. And this is kind of the basis of our entire atomic theory. Oh, you don't want that one. All right. Here it is. Okay, we'll make it smaller. All right, so this is kind of where we started with our atomic theory. And now, not all of this stuff is right. Today we found out and we've learned that a lot of it's different, but at the same time, a lot of it still does hold true, and we'll kind of highlight what those are as we go through. All right, his first one is that all matter is composed of very small particles called atoms. And kind of the way that you can think about this is imagine that you take a slice of cheese or a block of cheese and you cut it in half. And then you cut it in half again. And you cut it in half again. And again, and again, and again, and again, and again. Eventually, are you still going to be able to cut it in half? Well, no, okay, because you're going to get to a piece that's so small that, you don't have anything left to cut in half. Okay, well, that piece is what we call an atom. Okay, so they're these really, really, really extremely small particles. The second one was that atoms of a given element are identical in every way. So every single atom of gold is exactly alike to every other atom of gold. Okay, so they're unique with each one. Okay, his third one is that you can't break up an atom. Okay, so an atom is that smallest part, kind of what goes with number one. Okay, the fourth one, and this is kind of a big one. Okay, atoms of different elements combine in whole number ratios to form compounds. I'll show you an example of this in just a little bit. And then the last one, in chemical reactions, atoms are combined, separated, or rearranged, but that's it. Okay, now, the other thing that I want to add, and this wasn't actually typed in, but number two, okay, if an atom of a given element is identical in every way, that atom is going to be different from another type of atom, okay? A gold atom is going to be different, and it will never look exactly the same as a silver atom, or as a copper atom, or as a hydrogen atom. Okay, so it's kind of important to think about that. So atoms are unique with every other element that they're going to have, okay, of that size. All right, so we got a lot of stuff over there. Now let's kind of start to explain it a little bit more. Let's imagine that we have an element of carbon, right? Here is a carbon atom. Okay, and we're going to add to it an element of oxygen. Let's get a big old oxygen atom. Alright, so we got those two things. Well, if we add those together, in the end, what it's going to look like is that these guys will be, right, we got our carbon and we got our oxygen, okay, and they're kind of smashed together, right? Now, when we're looking at this stuff, let's make it small again, okay, if we have mass of X of this guy, okay, and then our oxygen, our mass Y, what do you think the mass of this guy over here is going to be? Hopefully, you guessed that it's going to be X plus Y, right? It can't be any more, it can't be any less, because those two things that went together have to equal up at the end, okay? And we could go backwards, right? If we were going to switch it around, I wonder if I can do it this way, right? Oh, look at that. Crazy. Okay, so if we switch it around, right, we start with two things, and we break them apart. Well, at the beginning, it's there, and then it kind of goes. Okay, so this is the whole idea of law of conservation of mass. It can't be destroyed, it can't be created. It just changes, right? It might start as one group, and then it's going to separate to two different ones. Okay, now, the law of definite proportions, as we go over this again, okay, that one's pretty simple. That's just what we're saying. If this was carbon monoxide, okay, so we have carbon and oxygen, this would be carbon, this would be oxygen. It wouldn't matter if we have a giant block of carbon monoxide, it's always going to have one carbon, one oxygen, or if we had a single molecule of carbon monoxide, it's still that 1-to-1. Okay, simple enough. Alright, let's get rid of that. Or at least make it small, we'll put it up there, kind of remind us that's what that looks like. Okay, the next one though, alright, I'm going to draw this one first and then we'll kind of keep going, is to show you that we have whole number ratios for everything. So that's that law of multiple proportions. Okay, and that they're always going to be a ratio of small whole numbers. So if we have carbon here, and we have oxygen here, and we have another oxygen, well, when this thing combines, right, we're going to get, let's make it big. Okay, we're going to get this guy, And this would be carbon dioxide. Okay, we'll fill in kind of those letters to make it easy. So that's carbon, oxygen, oxygen, carbon, oxygen, oxygen. And you can see that this is 1 to 2. Okay, and when they combine, we still have 1 to 2. Okay, and these are just the small whole numbers that we kind of go through with this. All right. And it's really not super complicated. It's just that these ideas, you know, this is where we started with the atom. And they're going to change, guys. As we kind of keep learning, we're going to see that all this stuff, you know, changes as we go, but it's all based on where we were given. So this is where we're starting with the atom. We will definitely change as we keep going. All right?